Hi everyone. We are going to continue with our lecture on this introductory course to quantum mechanics and computation. So today's topic is Dirac's notation. Is the third day of the program. Here we can see a little overview of what we are going to be discussing today. We have quite a busy day, I would say. I will also need to define a few more mathematical things that we will need in the future. But we are going to do that using the Dirac notation, right? So it's going to be good for us to see the stuff. So at first, I will introduce the ket notation because the Dirac notation it's also called the bracket notation. So firstly, I will introduce the ket. After that, I will speak about linear functionals and linear operators. After that, I will define the bracket notation. And then I will also talk about the adjoint operator, some exercises, and projectors. So let's begin. We have a lot of stuff to see. So uh, basically, ket ket notation is just a different way to write vectors in the sense that if normally in the last day we were writing vectors in this way. So now in the ket notation, we just normally write a vector using this way. Mhm. And it's just a different way of writing a vector, right? So and this expression is called a ket. When you write the vector in this way, it is usually called a ket. We will in a few minutes we will understand better the bracket idea, but this will come later. So, for example, you could a general linear combination in whatever Hilbert space, because we are always going to be working with Hilbert spacing from now on. For example, take this easy example, like very similar to the two-dimensional plane we were uh, discussing the other day. So this will be the general linear combination where alpha and beta belongs to the complex number plane. Hmm? This will be an example of a two-dimensional Hilbert space over the complex numbers. And this we will use at some point in quantum mechanics. Also, you this is more usual maybe to find this. This is a more general. Just to say that you have an n-dimensional space, because in here I'm just saying that I have m vector, right? This is the same as saying x1, x2, x3. Oh, I don't have a space until. Uh, mm, well, let me x2, x3, x4, right until xn, right, and now it's finished. This is a short way of writing this whole pseudonym. N could be 100, 20, 50. So we are not going to be writing x1, x2, x3, x4 until we get to the 100 or whatever. This is just a short way to write this. So a general linear combination using this basis here could looks like this. Hmm? I'm going to erase this. Look like this. It's just, it's the same as this. Just the difference is you have more elements. So you are going to have by multiplying more stuff. This will be the same as alpha one times x1 plus alpha 2 times x2, and you go on until you reach alpha n times x n, right? Using this symbol is the sound that we have already faced the first day. It's very useful, and it is used in almost every way, every day in order to do calculations and different things. So it's better to get used to this. So I hope this is fine. We're just writing vectors using this notation, and this is called a ket, as I have already said. So let's move on. All right. So linear functionals. This is not so fundamental, but is quite in order to deeply understand the bracket notation, it's important to have to know what is a linear functional. So I'm just going to define it here quickly. So a linear functional is just a function, right? A function that takes one vector out of your Hilbert space and it gives you a complex number, right? That is going to be your functional. It's just a function that takes a vector and gives you a complex number. That just would be a functional, right? But if you want a linear functional, it must satisfy these properties over here. Well, this property is just it must be linear. What is the meaning of linear? We have more or less just discussed this in the previous lectures, but if you have, because you have here your function, your linear function, you have here your vector, and it's a general linear combination of two different vectors, right? I have here one vector and the other one. I don't. They are any vector in your Hilbert space. It doesn't matter what vector they are, and you have a linear combination of both of them. If you have that input in your linear functional, it means that it will be the same as just the sum of applying the linear functional to each vector, and you can also take out the coefficient. And this is the linear part of the linear functional, right? So that's the condition it must satisfy in order to be called a linear functional. So these are complex numbers in general, and these are vectors, right? I mean, in here that should be the other one. Uh, 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 Sorry, there are some typing mistakes. uh, Also, some properties if you have two linear functionals acting on one vector, you can also write this. I mean, I believe this is quite intuitive. And also we will, I mean, instead of writing always the parentheses in order to indicate where we are acting, this is normal to just write it in this way. I mean, we understand that this functional is acting on this vector. Anyway, so there is one curiosity or important idea that I will highlight. I'm not going to detail on this because it could get quite difficult, I would say, or confusing. But you can also make another vectorial space out of your linear functionals. I mean, if you take your set of different type of linear functionals, you can create another vectorial space with the and a vector of that space will be a linear functional. And if you have a Hilbert space H, right, you can define like the space of linear functionals acting on that Hilbert space, and that's usually called the dual space. This is a little more advanced, right? So normally when something is more, I know it's more difficult to understand. I usually use the orange color, right? So you're going to see the orange color in a few slides here, but I mean, feel free to stop me at any moment, as I always say. Just write your question in Discord or in the chat, or open your microphone. Feel free to ask. So that's for the everything I wanted to say about linear functional. So let's move into linear operators. And this one, the linear operators are going to be more important I mean, like way more important, and we will understand that in the next lecture. But basically, a linear operator is, if you want to say, another kind of function, but it is a function that takes one vector in your Hilbert space and it gives you another vector in the same Hilbert space. I mean, it just acts on a vector and gives you another vector of your same space. So here, and in order to be called linear operator, must satisfy basically the same operation that we were talking before. I mean, you have your operator acting on a general linear combination, and these are just general vectors. I mean, don't have to be satisfy any condition, any vector in your Hilbert space. So if you have this, I mean, your operator A acting on a general linear combination, you can decompose it in this way. Yeah, take out. You can decompose the sum in two terms, and also take out the complex numbers. And this is the linear operator that is basically the same as we were discussing before for any complex number and for any vector in your Hilbert space. So this is also the same property. If you have two operators acting on a vector, it will give you these two different vectors. And also, if you have three operators, this it satisfies this property, right? That if you, it doesn't matter whether you apply this or you apply this. I mean, you can't compose the operators as you want, as long as you don't change orders, because there is here an important something that is quite important to highlight, and is that linear operators, they don't commute in general. And the meaning of that is just this expression here. I mean, uh, if you have two operators A and B, it's not the same. It's not the same as B and A. In general, this is not true. It can be true depending on the operator, but in general, you cannot say that two operators are going to commute, right? And this, I mean, this is a key point in quantum mechanics, I would say, because well, we will understand why this is a key point in the next lecture. But believe me, that quantum mechanics wouldn't be the same if it weren't about this interesting property about there are some operators that commute and there are other operators that don't commute, right? So like keep that in mind. Uh, Here, a little example. Let's take this basis, right? So in this basis, this is just, remember, this is ket notation. We are just writing vectors and usual. So in this basis, we could call this vector 1, right? And write it in this form. And we can also call this vector 2 and write as a column right here. So if we have a general linear combination, our general vector could be this one, this guy here. Very well. So imagine that I have a linear operator that acts on this on the basis in this way. I mean, I define it this way. This is just an example, right? I mean, there are lots of different operators, linear operators. So let's say I define my linear operator in this way. So you can find the matrix of your linear operator by just using this definition, and the matrix will be this one. I mean, I guess it might be a little difficult to understand at first, but there is a key point here that I haven't mentioned in the slide, and this is must be an orthonormal. Orthonormal. No. This must be an orthonormal basis in order, because remember the last day when we were talking about orthonormal basis. I mean, I did speak a little between all the definitions of norm and distances, everything. I did talk about orthonormal basis. It just you have your vector must be orthogonal and also have norm one, right? So from now on, I will always be working with orthonormal basis. So if you have an orthonormal basis, you uh, you define this operator in this way. You can find that the matrix is going to be this one. So because at the end, what you are doing is just changing the x vector into the into this one, and also this vector into the x1. So you're just like changing the basis. So if you apply that to, you can do in both way. I mean, you can just look at this definition here and go straight and apply that. I mean, you have f over your general linear combination vector. So you apply linearity. I mean, f is going to be applied to the x vector and this other one, this other vector. And this is just uh, this one, and this is this other vector. So at the end, you have this. And if you see, I mean, like this definition here, this is going to be the same as this one. If you don't want, if you prefer to do the operation using the matrix notation, you can also do that. It's fine. You just have to put the matrix form of your operator, of your linear operator, and the matrix form of your vector. And you apply matrix multiplication, and I hope that everyone is familiar with matrix multiplication. So basically, just in case, this will be multiply this with this, so it will be alpha times 0 plus beta times 1, so it will be beta, right? Uh, and also this multiply this by this, and will be alpha times 1 plus 0 times beta, and it will be alpha, right? So you can either work with um, a straightforward calculation with just vectors notation, right? Like using kets, the definition of your linear operator, or you can use the matrix representation. Take care that in order to use the matrix representation, everything must be written in the same basis. Because I don't know if you remember from the other day that you can write the same vector using different bases. So the matrix representation can't be different depending on the basis that you're using, but the vector is the same, right? So in order to use matrix representation, in order to do any calculation, you need to have like the representation of your vector and your operator, they must be in the same basis, because if not, you are going to get a wrong result. Fine. So I hope this example might help a little understanding what is a linear operator. I know it might be a little confusing to understand why this matrix. I mean, if you can ask me maybe later in the Discord after the lecture or whatever. So, well, so let's go into the bracket notation, right? So, normally, people, it depends on how deep someone wants to understand this, but and a lot of when you discuss lit at some point as really an introduction, they don't usually talk about this stuff because it's like more difficult to understand. And I'm just going to try to explain it in easy way, like saying the key points, that so you can maybe in the future look for yourself and try to understand better. But the idea is what I'm going to explain right now. So you have your Hilbert space here, right? You have your Hilbert space is the blue. I have represent, like this is just a graphical representation. Is that doesn't have really a special sense. So you have your Hilbert space here represented in blue, and here you have your cats, right? Your cats or cats in plural. So you can define the dual space. And this is related with what I have said before about linear functionals. And linear functional can also make a vectorial space. So we are going to call, um, let's say, let me write. So if you have a set of linear functionals over a certain Hilbert space, you can find that there is a relationship between each element of these two different spaces. I mean, you have your Hilbert space and you have your dual space. For each element of your Hilbert space, there is another element of your dual space that is related in some way, right? In some way. And in some way is more complicated than just in some way, but let's take that for now. So we are going to define, let's say, an operation, right? That is called the adjoint operation, and is denoted by this dagger over here. And this operator takes your Hilbert, I mean, the vector in your Hilbert space, and gives you the corresponding vector in your dual space, right? This other vector that and we denote in this way, this will be the corresponding vector in the dual space, that is another space, right? That has some relation with our Hilbert space. This other vector is called bra. Right, this is the bra, so we have the bra and the ket. That's what, that's the reason that it's called bracket notation. Uh, so so far so yeah, I have it here. I have it here. So that's the ket and that's the bra. Fine enough. So for example, let's say you have here another general linear combination in your Hilbert space. The corresponding and this would be the bra. Hmm? Right. Let me write it more or less. This would be the bra. Oh my god. Yeah, I didn't write it that good. Yeah. So this will be the bra. An important thing is that when you apply the adjoint operator, your complex number, you have to apply the complex conjugate. Mhm. Let's take that as a property of the adjoint operation. I mean, here I'm defining that join in this way because I feel like it's more easy to just say this is like this instead of trying to understand why this is like this, since this is like an introductory course for high school students. So I'm not going to go that deep, but just let's take this definition in this way. So the idea is you have your kets that are the vectors in your Hilbert space, and you can also define the dual space, that is an space that has some relation with your Hilbert space. So you can find a vector in the dual space that corresponds to another vector in your Hilbert space, as I have represented here, and that the vectors in the dual space are the bras and are we write them in this way. So writing this in this form is quite useful because yes, now we are going to define the scalar product that we are going to be using in the following lectures in quantum computing also. So this is not the only way. I mean, in quantum mechanics, depending on the system, on the properties, yeah, or of the quantum system, the scalar product can change a little, I would say. Yeah, a little or not a little. But we will mainly use this form, and this is going to be like quite similar to the scalar product we are used to work in this toy example we discussed the other day, that just multiplying the coordinates, right? Like x1 times x2, like plus uh, J1, J2, right? So let's try to understand this. So let's say I have vector A that is going to be a linear combination of these two vectors, like the basis we are using in our two-dimensional example. And I have another vector here in, of these two are vectors in my Hilbert space, right? I mean, the A and B are vectors in the Hilbert space. This is the H for the Hilbert space. So if I use the matrix representation, this vector will look like this. Same is the same as we have done before. But when we use the bra vector, let's say the bra vector, we have to do as same as before. We have these bras here, and also we do the complex conjugate. But uh, something that maybe I could have explained here better. Let's I want to zoom a little. So basically, what we do here is this vector is in the matrix representation is written as 1, 0, and this other vector is written as 0, 1. So uh, maybe I should have said this before, but we will discuss this also later when we talk about the adjoint operator. But when you apply the adjoint operation, like we have just seen, you have to transpose the matrix. I mean, I guess if you have some matrix knowledge, you know what is the transpose of a matrix. So we are just doing that here. And apart from that, do the complex conjugate. So you get this vector here, right? So if we have that, and I hope it's more or less understand. I mean, I know there are a lot of things that are just this is like this, and you may be wondering why this is like this, but this is it would be, I would say, out of the scope of this course. So let's say we have this vector and this other vector written in this way. So we can write down this expression, and this is the bracket, right? So you have a bra and a get, or yeah, bracket, and the bracket is the scalar product. I mean, is the way we are going to be writing the scalar product in the sense that this is maybe I should have yeah the scalar product. So this is a scalar product of A and B, right? This is the way that we define the scalar product, and you will see that it's quite uh, reasonable in the sense that take the matrix representation. For example, you could also do this without the matrix representation, but uh, I have done it using the matrix representation. So take the vector, just write down its matrix representation, and also for the A vector, and just multiply. So this will be multiply this and multiply this, right? In this order. So we will have the first coordinate times I mean the first coordinate of the first vector multiplying the first coordinate of the first vector plus the same second coordinate of the second vector and times the second coordinate of the. Oh, I have I have confused a little, but I guess you understand the idea. I mean, you are just multiplying. This is the same that when we were defining. I mean, in our example of the two-dimensional plane, right? We were just saying like this is will be okay. This is going to be x1 times x x2 plus j1 times j2, right? It's the same. The only difference is that we are working with complex number, and in here we are doing the complex conjugate to the uh, uh, complex numbers of your first vector. That's the only difference between this scalar product I'm defining right now and the scalar product that we were seeing the other day. So I hope this seems logical and intuitive in the sense that it's just like the same idea, but like more general, and also using the bracket notation. Mm, well, I, I hope that that's clear enough. So here down here I have another example, maybe a little more complicated. And remember, I mean, this will be the with the basis I have writing on more general basis, right? From I equals 1 to n, right? So if you have these two general vectors, and for this I remember we need orthonormal basis, right? Vectors. Every vector must be orthogonal in the basis to the other ones, and every vector must be normalized. I mean, they have their norm should be one. That's an important property. I'm going to be always working with that type of basis, but I remember just in case, right? Uh, so you have these two vectors, the scalar product. It's going to be denoted in this way. I mean, it's the same. It's just the bracket. And in this case, I have put this vector like the first one. So you just multiply the corresponding coordinates. I mean, this will be basically the same. This, just in case, this is A1 complex conjugate B1, and you sum until you get AN complex conjugate BN. Right? This is just an easy way to write a lot of summing terms, right? Because imagine you have n equals 100. You are not going to be writing every number, right? Right? So that's why we usually use this and other different mathematical symbols. So this is going to be our scalar product. I hope everything is understandable. This is quite important to understand, I would say. So yeah. So this is just to point out a few things. So this is the same example we have just seen. The scalar product can be called bracket, right? Or maybe without this, like just bracket. I mean, it doesn't matter. I mean, people will understand you, right? You can use different, slightly different names, but the idea is the same. So this is just, I would say, complementary in the sense that I know it's a little more difficult to understand. But I told before that I have, when we were discussing here, that you have your Hilbert space and you define the dual space, and the dual space is related to linear functional, right? So uh, when we talk about the bracket, what we are really saying is that the bra, that is a vector of the dual space, is a linear functional acting on the ket. And that linear functional is acting on the ket, giving us a complex number and that complex number is going to be the scalar product, right? That's basically what we are saying. And there is an important theorem that is the theorem that makes this possible, or I mean that proof that this is like something we can do. So, and that is called the Riesz representation theorem that I'm not going to announce because it will be quite confusing. But I just wanted to say that because in order for you maybe in the future when you want to go deeper into to have a deeper understanding of this, you can maybe check this. Take some time because it's I know it's quite difficult at first to understand these topics, but these are just complementary notes. I I would say, yeah. So let's move on because we have yet a lot of stuff to discuss. Oh my god, we can use yeah. So another important thing is that we cannot just use like a bracket like to the scalar product, but we could also use the ket bra, and the ket bra will be something like this. So this is the cat. This is the cat, right? And this is the bra, right? So a very straightforward way to see this is you just use the matrix representation and remember that I have said that when you do the bra, right? You have to transpose the matrix. So the bra will be something like this. Yeah. So if you do that and you calculate this expression, for example, you just will have these matrices. This will be just to make sure it will be X. This will be the bra. It will be would be right. And if you do the matrix multiplication, I mean, you multiply this by this, you get 1, multiply this by this, you get 0, and you do matrix multiplication, you get this, and this could be a linear operator, right? I mean, you can write linear operation in this way, and this will also be useful in linear, in quantum mechanics, for a lot of things, right? So let's move on because there are more things to explain. We have 20 minutes. Uh, Very well. So, adjoint operator. This is another key idea in quantum mechanics, and we use this like a lot. So I hope, but it's also at first, and also with the notation, it's also it's something that it gets difficult to understand. The only way I would say you will have a better understanding and get comfortable with this is just practicing and looking exercises and that. So that's why I have a few exercises after this. But anyway, it would be enough to feel comfortable with this. But anyway, because what's the problem? The problem is that we have imagine you have a vector, right, in your Hilbert space. So if we have a linear operator acting on that vector, let's say a linear operator takes a vector and gives you another vector. This means that this guy here belongs to your Hilbert space also. So what if you can do the adjoint operator in to your vector, you could also do that join operator to this other vector because I mean you could say this is another vector called W, for example, right? You could say W, right? This is another vector. So you could do this adjoint operation. And what would be the result of that adjoint operator since you are applying a linear operator on your vector and you are getting another vector that is exactly, it is not a special vector, right? I mean, it's like any other vector in your Hilbert space. So we denote this in this way. Mhm. If we have that join operation acting in this vector, we write this. We write this. This is the bra that we have already discussed a little, and this would be the adjoint operator. And what is the adjoint operator? So in here, I'm also going to define this in a easy way, in the sense that it's not the most precise or maybe mm, the best way or more mathematical. Uh, I don't know, a mathematical correct way to define this, but is the way we are going to use this in quantum computation. So if you have a linear operator in matrix representation, and let's take a bidimensional example, the adjoint operator is going to be just you have to apply this operation to your matrix representation, and you have to transpose. This is the transpose that we have already talked about, and apart from that, you have to complex conjugate the the whole matrix, right? So you have this matrix, you transpose, and if you transpose, you are just going to change C and B in this case because the bidimensional case is quite simple, and also complex conjugate everything. That's what the adjoint operation or the adjoint operator is going to be like when you apply that to a linear operator in our case. Fine. I hope that's understandable. And also be careful because we will write, for example, because for example, let's say you have this bracket, right? Because this is, you could call this uh, W. I mean, this, and this will be the same as this bracket here. I mean, because this is another vector or your Hilbert space. So be careful here because the notation is quite confusing sometimes. So if we write this, you will may wonder, all right, this operator is acting on this guy or this guy, right? What's what I mean? What are we acting on? So, and this way of writing this operation is basically a way of writing these two operations here. So it can add on the first element in this way. I mean, it just take this. mm, would be the A over the first vector, or it could add on the second vector. But in this case, you won't be acting with A, you will be acting with the corresponding adjoint operator. I hope that's uh, uh, that's basically how it is in the notation. I don't feel like there is much to explain here. Just it's important to understand that. Here I have a few. I don't know. Okay, another more remark. I can also go, but so this is an important concept. I mean, this is you have a joint operator of a general idea. Like for every operator, you will be able to define your adjoint operator, right? But there might be a special operator that satisfies certain properties, and in this case, if an operator satisfies this property, it will be called a self-adjoint operator or also Hermitian operator. And the difference between self-adjoint operator and Hermitian operator is going to be zero for us, but it's not exactly zero because it has to be with the dimensions in the system, because you could go to infinite dimension Hilbert spaces that we are not going to work. And in that case, things get a little more difficult. So you cannot define things like I'm doing right now, because when you are working with infinite dimension system, you cannot use matrix representation. Some things get a little weird there. But for quantum computing, or at least what we are going to do in quantum computing in this introductory course, we are not going to need that. So we just work with this. So let's say Hermitian operator or self-adjoint operator is going to be the same for us. Uh, right? So self-adjoint is basically that if you have an operator, the adjoint operator is the same as, as your original operator. It's just that's the self-adjoint operator. Uh, so just to take an example, a general way of writing every self-adjoint operator in your bidimensional space in matrix representation could be this one, right? Where A and C are real numbers and B belongs to the complex numbers. Um, I will leave you as an exercise if you want to check why if you write a matrix in this way, you will always it will always satisfy this condition, right? Uh, you can check that. It's not difficult. Just apply the operation I have defined in the last slide. Also here, another result is that if you have a self-adjoint operator, it will this identity holds, right? Uh, It's just a result. I mean, we are going to use this a little in the exercises, and I will try to explain maybe this a little better. So since uh, yeah, so let's put some practical work. So let's try to prove this, right? So in order to prove this, I mean, you could maybe call this an operator, right? So a dagger would be just what we want to compute. Mm, very well. I mean, I have just defined this in this way to make clear that this is just an operator. We don't exactly know because this is for any. I mean, I haven't specified here, but this is for any. I mean, these are any vector in your Hilbert space. They don't have to satisfy any property. So take two other vectors, let's say alpha and beta, in your Hilbert space. Um, and let's calculate this. Mm, right? Let's write this down. So um, basically, this will be the same as uh, this one here. Yeah, I have to just write this. Here. Yes. This is just this, and in here I'm going to use the definition of a triangle, and the definition will give me mm, that this is the same as b alpha here, and this is going to be complex conjugate. Uh, Maybe in order to understand this, well, let me finish. Maybe I will discuss this step a little more. And when you have this, you just apply. When you have an operator defined in this way, the bracket notation is quite useful because you can just write this, right? I have just uh, do the bracket here and the other bracket here, also the complex conjugate. I'm applying the complex conjugate to each of these scalar products because these are scalar products. Remember that. I just uh, change the order of the scalar product. That's a property we discussed the other day. Mm, very well. So since this here is a scalar product and this is another scalar product, so these are just numbers. I mean, I can change the order because these are just numbers. So I can write this. And finally, I can also write this. So at the end, we have just finished the exercise. I will highlight orange, maybe orange. We have this expression. No, we have this expression here and this other expression. We have the same uh, alpha and beta here. So the yellow part must be the same since this is an equality. Uh, yes. So I don't have a small space. I will try to move this a little. So we have proof. Mm, well, sí, yes, that this is equals uh, to this. I mean, I I know this is quite more difficult to understand, but give it a try as after the lecture. Also, trying to understand the previous scenes that I have defined. Uh, if you have any doubt after that, we can discuss on the Discord server for sure. Here I have another exercise. I don't know. I mean, and there are a little more stuff to discuss, but this is not so long. So we have an operator. I mean, we will take a little more than an hour, but I hope that's okay. Uh, we have an operator that acts on a vector and gives you the same vector, but is multiplied by a number, right? Then this is, in general, this is going to be a complex number. So we want to prove that if this is true, then that the join operator acting on the graph is going to be acting in this way. I mean, that this number is going to be the complex conjugate of the first number. So in order to prove that, we are going to, let's say, another vector that I mean, another general vector that I don't know. I mean, just any vector of your Hilbert space, your operator A, and this vector phi. I mean, this vector is this one, right? That's important. And let's take the complex conjugate of this expression, right? So this, by definition, again, and this is what the same I have done here, is going to be this. And this is where I get that the adjoining thing can be confusing with the notation, but things are like they are, so uh, very well. So if we have this from here, mhm, I could say, okay, I apply the operator into my vector. Mhm. And if I do this, I get this, right? By by definition of how the operator acts on this vector. So I will get A and the scalar product of this guy. And this is going to be, I'm not doing anything here. This stay the same. It's going to stay the same. But maybe let's move this. Well, no, it's fine. All right, so we have this. Fine. So now I apply the complex conjugate. Complex conjugate here. Change the orders here. Uh, yes. Yes, yes, yes. So at this point, we have basically solved the exercise since we have in this vector here. Let's highlight something. I mean, and this vector is the same and is for any vector in your Hilbert space since that is, since you have that for every vector in your Hilbert space, you can say that this equation is true. I mean, I'm just taking this and this, right? And that's what we wanted to prove. But yeah, it didn't take so long. Right, so this is just a little exercising on using bracket notation and with operators and stuff. I mean, this is like a big deal in the sense that I'm going really fast in this because I just, I mean, in this introductory course, I have to start talking about a lot of stuff. But at the end, when we get to the quantum computing, I believe it's not going to be that hard. And this is like speaking about general abstract things that is a little more difficult, I would say, than actual quantum computing because we will working in concrete examples and not so because this is more a mathematical proof rather than any physical exercise, right? So you just proving mathematical properties is normally more difficult than just doing exercise related to some physical thing. It depends for sure. It depends, but in quantum computing, when we do that introductory part, it will be easier. So I hope that you have see a little how to work with these things, and we are just going to be dealing with one more thing. And in order to introduce this, I am going to go back a little to our first simple example that are I want to introduce projectors, right? So a projector is going to be a linear operator. But before saying that, I want to get the intuitive idea of what is a projector and what we are doing when we say I'm projecting this vector into this other vector space or something like that. So imagine that you have your vector B, that would be this vector over here. So you have I don't know how you call this in high school, but I will call this the X projection, since it's the part of the vector that is on the X axis, right? And I could also call this the Y projection, since this is in the Y axis, on the vertical axis, whatever you want to call it, right? Uh, at the end, the idea about projections is that if you have a vector, you are trying to find uh, the part of that vector that is inside of the space generated by another vector. And I explain myself better. Uh, the x-axis is the space, just one-dimensional space, but a space generated by the x vector, if you want. So let's say with the notation we were using, your x vector generates the whole x-axis, because with the x vector you can generate the whole line, right? Multiplying by it. So the projection over the x space or the x-axis or whatever you want to call it is going to be the corresponding vector that is forming your original vector. So I don't know if I have confused more or no, but the idea is quite simple. So if you have this vector is 4 and 3, and you have your vector here, the project you can calculate the projection out of the scalar product, right? Because if you do the scalar product in that we define in the last day, you can easily see that this will be 4 and this will be 3, and this is basically this number, right? The number in the corresponding space generated by the x vector or in the vertical plane or vertical axis, or right. So taking that idea of with the scalar product, I get the corresponding projection. I can do that with the bracket notation and our quantum system. Right. So just this is a reminder of things we have already said. General linear combination. You can write the vector in this way. You have your basis of the Hilbert space. You have your scalar product that we have also defined previously. So let's say you have this vector and you calculate the scalar product with x, that is the first vector in your basis, you will get a1, and ay will be the projection onto that space. Also the same for the second vector in the basis. So if you want to create an operator that gives you the corresponding vector, it will be this one, right? I mean, this will be the linear operator that takes any vector and gives you the corresponding vector that is, and that's the corresponding vector that is going to be the projection in this case the x-axis, right? So if you apply this projector into the vector A, you are going to get this. This is the scalar product, right? So that's why the Dirac notation is usually useful, because you write the operator in this way, And when you apply the operator into another ket or another vector of your Hilbert space, you can write this directly like the scalar product. So this is going to be A1, right? So this will be the corresponding vector in the space generated by the vector X. And this is the projection, right? And the very same happens with you if you do that with the second vector in your basis. I hope that's understandable. Mm, right. Yeah. This is the last slide for today, and this is also something that it might be a little more difficult to understand. But anyway, seeing about the Hilbert space with uh, any amount of elements in the basis, like m vectors. So, and remember, I mean, I haven't said this before, but this is the way of writing an orthonormal basis. Remember the symbol we explained in the last lecture? So this will be the way of saying that this is orthonormal basis. Orthonormal basis. So, for example, you could want to project into a bigger space. I mean, just not projecting in one direction, but you could maybe want to project in you to find the projection of your vector in a bigger subspace of your whole space, because the whole space is generated by these guys, but you could be interested in a little space that is inside your whole space, right? I mean, if you have H here, I could maybe have a little space here called H prime that is just generated by these guys, and the selection of this vector is random. I mean, I could have chosen x5 or x26. I mean, I just chosen three vectors, random vectors. So the projector onto this subspace inside your whole Hilbert space is just the sum of the projector of in every direction, let's say, right? Like if you want to project over this direction, this will be the corresponding projector. This will be the other corresponding projector. So you sum the projectors. Finally, one more idea, and this one is it's I believe more complicated, but extremely important and useful is the completeness. I cannot I can pronounce, but this relation here, uh, that's the basically is this identity. So here you have the identity matrix that is just like the neutral element, yeah, like one in like if you are working with numbers, it would be the one. Is that if you multiply any matrix by the identity matrix, it will be the same, right? So if you have an orthonormal basis of your Hilbert space and you sum over every projector in your space, you get the identity. And the intuitive idea with this is that, I mean, at the end, a projection is just if you have your original vector, you are taking parts of that vector into different spaces, right? You have, let's say, yeah, any vector. For example, yeah, in this is example, this is this could be, for example, x, the projection over the horizontal axis if you apply it to your vector b. Right? Like, so this will be b in the bracket notation, and will also be the projection over the vertical axis b. So if you do this, and this is summing all the projections, in this case we have two-dimensional space, this would be summing over all the projectors in your space. If we have this over B, you can check that this will be the same as B. So this here is the identity, right? This is basically what I'm saying here, that if you sum over every projector in your basis, like in the orthonormal basis that you are using, it's going to be the identity. And this is quite useful because, for example, you have your vector A, so you can introduce this expression because this is like multiplying by one. Understand that if I add this whole sum into some expression, it's like multiplying by one. So I can do that without doing anything else because it's just multiplying by one. Yeah, so I do that, and we have here the scalar product. So it's a way. I mean, at the end, I get the general linear combination that we have been discussing a few times, right? Just multiply a coefficient times the corresponding vector in the basis. But now we can see that this coefficient depends on the basis that you are using, right? If you change the vector x, the coefficient won't be the same because what is the only thing that stays the same is the vector. The vector doesn't change because that's the abstract thing that is going to be the same, the element of your Hilbert space. But depending on the basis you use, the coefficient will change. Um, that's everything, right? So this is the end. I have taken a little more time, but not so much. So I hope that's fine. Here, as always, a reference for you to deep a little more. I I hope that at least, I mean, I know that probably uh, you won't have understood everything deeply, but the idea is to have the key concepts in your mind to try to start working on them, practicing, maybe looking some exercises on the internet. I can provide more exercises in case you might be interested, and also using these references. So see you the next day.